Okay, welcome to chapter 4, part 2, sections 4.4 to 4.7. This is the second and last part of our trigonometry review. We will be reviewing other things from trigonometry, but this is the last full section that should be at least mostly review. So we're going to look at basic waves, or which are called sinusoids, and their transformations a little bit. And then we're going to look at the graphs of the remaining trigonometric functions, including the reciprocal and inverse functions. Why do we care? Because sine and cosine gain added significance when used to model waves and periodic behavior. So again, we're going to be mostly studying the graphs of them. But then when we come back after Christmas break, we'll look at a lot of applications for these things. So the first thing that I want to review is the graphs of the sinusoids. So sinusoids are sine and cosine, and they're called sinusoids because they have really the exact same shape. They're just shifted over from one another. So if you look at cosine, its maximum is on the y-axis, and you look at sine, it's exactly the same shape, but its maximum is shifted over right by pi over 2. So if we look at the y value for the maximum, it occurs at an x value of y or pi over 2. Okay, and if we look at our graph of cosine, that same value of pi over 2 is now not a maximum, but a 0. So we're looking at these graphs, and they're each transformed by sliding one or the other over by pi over 2. So to get from cosine to sine, we would have to shift pi over 2 to the right. To get from sine to cosine, we would shift pi over 2 to the left. So one key, and we'll talk about this in more detail when we go into identities, but one way that we can write sine and cosine in terms of each other, because we know how to write a shift for a function, we can say that sine of theta equals, or think about y equals cosine shifted to the right. So cosine, to shift sideways, we're going to add or subtract to theta. To shift to the right, we're going to subtract pi over 2. Or we can say that cosine of theta equals sine of theta shifted to the left by pi over 2. So that's one way that we can use transformations to see the relationship between sinusoids and to see why sine and cosine have the same name for their graph. The shape of the graph, that wave shape, is a sinusoid. Now, some special properties of these graphs. Notice these waves have a height. The height of a graph from the center to the top is called the amplitude, and we'll define that formally on the next slide. They also repeat. Notice the wave repeats itself. So from one place, the entire shape of the graph before it repeats itself is called the period. That's labeled by t. It's called the period of the function, which is how often does it repeat itself, or how long before it repeats itself. And then our other kind of special property here is the frequency. How often does it repeat itself? And the frequency is always 1 over the period. Because if it takes, for example, let's think about a racetrack. If it takes 500 meters before you're back at the beginning of the racetrack, then that means you can go twice before you get to 1,000 meters, right? So frequency is how often does it happen. The period is how long before you start repeating. They're opposites of each other. So we have the period is t. We use t to represent period, which is how long before it repeats itself. And then frequency, which is 1 over t, is how long before it repeats itself. Okay. So, here we go. The period of a function, if there's a positive number c such that f of t plus c equals f of t. So notice this means that f of t is repeating every c units. The smallest number c is called the period of the function. For sine and cosine, the period is 2 pi. And I have a summary slide at the end that will show the period of each of the functions. So for sine and cosine, the period is 2 pi. Okay, a sinusoid is any graph that can be written in terms of sine, and we just saw on the last slide that sine and cosine can be written in terms of each other. So cosine is also a sinusoid because it can be written in terms of sine. So essentially, a sinusoid means the parent function can be sine. Okay. Oh man. There we go. Amplitude of a sinusoid, that's the height from the middle. So when we're looking at sine and cosine, if we look at from the middle to the maximum or from the middle to the minimum, those are the amplitude of the wave. Now, it doesn't always have to be centered across the x-axis. If I translate my sinusoid up or down, for example, maybe I have like this, then the amplitude doesn't change to the x-axis. It's always from the middle to the height and from the middle to the maximum and the middle to the minimum. So we can take max minus min divided by 2. Okay, the period of the function is how often it repeats, right? So the period of a sinusoid is going to be 2 pi if it's not transformed. And then if we stretch or shrink it horizontally, that will change the period. And so we can divide by the absolute value of b. Remember, b is how much it has been stretched or shrunk, but it's a horizontal transformation, so it happens backwards. So 2 pi divided by b gives us the period of any sinusoid if it has been stretched or compressed horizontally. Our standard sinusoid function has a period of 2 pi. Okay, so summary, graphs of a sinusoid can be written with a parent function of sine or cosine, because cosine can also be written as sine. It has an amplitude, absolute value of a. Amplitude is the distance from minimum or maximum to the midline. So that's half of the distance from max to min. The period is how far does it go before repeating itself. So that's 1 period. Here's a second period, which is standard 2 pi. If it has been horizontally stretched or compressed, we have to divide that by b. And the frequency is how many periods fit into 1 unit length. So that's the reciprocal of the period. So if we call this t, then this is 1 over t. Okay, now we have a couple of additional properties that we can talk about. Amplitude changes with vertical stretch. Period changes with horizontal stretch. What about shifting? If we shift horizontally, that is now called phase shift. Phase shift is exactly the same. It's just another name for horizontal shift. Okay, and then we don't have a special way of naming the vertical shift. It's just vertical translation, vertical shift, still determined by K. So transformations, nothing has changed since we talked about these in chapter 1. Everything is still the same. However, now we have some additional vocabulary that we can use specifically for sinusoids. Our third trigonometric function is tangent. For tangent, it's sine divided by cosine. So if you look at our graph here, the red graph is cosine of theta. And the reason I graphed cosine with tangent is because there's this special relationship. Since cosine is in the denominator, and we know that the denominator cannot be 0, every time cosine of theta is 0, we have a vertical asymptote. So when cosine of theta is 0, we have a vertical asymptote. And notice that happens at all of our pi over 2s, pi over 2, 3 pi over 2, 5 pi over 2. So the way we can say that is odd pi over 2, because if it's an even pi over 2, it would simplify, right? If I had 3 pi over 2, there's a horizontal asymptote. If I have 4 pi over 2, no horizontal asymptote, that's actually a 0. So our even pi over 2s are where tangent crosses the x-axis. So I can say pi over 2 plus pi k. And these are vertical asymptotes, vertical asymptotes. So that's x equals any pi over 2 plus pi k. And for the zeros, we know that x equals 0 at pi plus pi k. So multiples of pi are zeros. Multiples of pi over 2 that are still fractions are asymptotes. We can also think of it as asymptotes when cosine of theta is 0 and zeros when sine of theta is 0. Right? So these are properties of tangent that hopefully you've seen before. That's why I'm going through them pretty quickly. Our next function that I want to take a look at is the cotangent function. So just like tangent, cotangent is a ratio of sine to cosine. So this time it's graphed with respect to sine. So the red graph here is sine. And that shows us that now our asymptotes are when sine of theta is 0. And our zeros are when cosine of theta is 0. When sine of theta is 0, we're looking at our multiples of pi, our non-fraction multiples of pi. So again, we say that x equals pi plus pi k. And then cosine is all of the fraction ones. So that's pi over 2 plus pi k. Pi over 2 plus 1 pi, which would be 3 pi over 2. Pi over 2 plus 2 pi would be 5 pi over 2. So notice that this setup gives us all of our multiples of pi over 2 that don't reduce. Okay. I also want to show you this on a unit circle. So if I'm looking at sine is y and cosine is x, right? So cosine divided by sine, I can't let y equal 0. So y not equal to 0 on the unit circle. So that means undefined every time my angle is on the x-axis. So undefined when theta is 0, when theta is 180 degrees or 360 degrees, or pi, 2 pi, 3 pi, 4 pi. Okay, we can look at the same thing for tangent as well. We can look at how our graphs relate back to the unit circle. And I have an exploration posted on Blackbaud if you want to have a more interactive way of seeing these functions related to the unit circle. Okay, next let's look at secant. Secant is the inverse of cosine. Remember, each reciprocal, one of them has a co. So secant has no co, so its reciprocal is cosine. Of course, there are other ways to remember that, but that's one of the ways that I've found most helpful. And again, we're going to graph this with respect to its reciprocal function. So we're looking at all of these with respect to the denominator, because that's the one that gives us the asymptotes. So 1 divided by cosine, I'm looking everywhere that cosine is 0. We have a vertical asymptote. So when cosine is 0, our angle is multiples of pi over 2. Cosine is 0 at multiples of pi over 2 that don't reduce. So asymptotes are when cosine of theta is 0. And that's when x equals pi over 2 plus pi k. So that's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, all of the odd pi's over 2. The zeros would be when our numerator is 0. 1 never equals 0, so there are no zeros. Secant will never cross the x-axis. Okay, secant also has a period of 2 pi. I didn't talk about the period for tangent and cotangent. It's all going to be on the final screen, but let's go back and look at tangent and cotangent really quick. If we look at cotangent, notice the difference here is that cotangent has the same shape twice, 3, 4 times in a row. So the period for cotangent is actually pi instead of 2 pi, because what happens when we're looking at the unit circle is that quadrants 1 and 2 repeat themselves in quadrant 3 and 4. So cotangent in quadrant 1 is equal to cotangent in quadrant 2. Each of these reference angles have the same cotangent values. That's why cotangent is periodic twice as frequently as sine or cosine. Okay, so we saw secant. Let's look at cosecant. Cosecant relates to sine of theta. We're looking at wherever sine of theta is 0, gives us an asymptote. And that happens at the multiples of pi. Writing these in kind of the same format where I find the first asymptote and then I find out how frequently they move. A simpler way to write this would be just multiples of pi. Okay, but that doesn't really show us the first asymptote is at pi, and then every pi units, there's another asymptote. So that's why I'm writing it in this way, in case you were wondering why I didn't simplify that expression. Okay, again, for zeros on cosecant, it would be when our numerator is 0. Our numerator never equals 0, so there are no x-intercepts for cosecant. The period for cosecant is 2 pi. Okay. So here we go. This is the slide that I told you. It has the periods for each function: sine, cosine, tangent, cotangent, secant, and cosecant. I put them in the same order that we looked at their graphs. We can also talk about their domains. Sine and cosine had no asymptotes, so their domain is all real numbers. Tangent and secant both have, let me write our fractions here. This is sine over cosine. Secant is 1 over cosine. So they have the same asymptotes because they both have cosine in the denominator, and that's why they have the same domains. And then cotangent, which is cosine over sine, and cosecant, which is 1 over sine, have the same denominator, and that is why they have the same domain. They have the same asymptotes of when sine is 0. For the range, sine and cosine come directly from the unit circle. So if I'm looking at x and y values on the unit circle, my largest x value is 1, my smallest x value is -1. So my range for cosine has to be between -1 and 1. And then the same thing for sine, my highest y value is 1, my lowest y value is -1. So the range for sine is also from -1 to 1. For tangent and cotangent, we're looking at a ratio of numbers, meaning if I have a bigger numerator divided by a smaller denominator, I can have any real number. Those numbers will continue out to infinity. I can get infinitesimally small in the denominator until I hit 0, which is where I get that asymptote. So these have all real numbers. Those will continue on, kind of similar to a cubic function, but periodic. Okay, and then secant and cosecant both have this kind of U upside down U shape going on. So they just have a gap in their range where sine and cosine would fit perfectly in between. So their range is from all of the numbers except for the numbers from -1 to 1. Okay. And then we can look at, so we looked at the properties, where those properties come from, the asymptotes and the zeros. We already talked about our last property here, even and odd, that's talking about symmetry, right? So sine, and I'll do a little sketch here. Sine looks like this, is symmetry with respect to the origin. So that's odd, origin is odd. Cosine looks kind of like a mustache. Cosine has symmetry with respect to the y-axis, so it is even. Tangent. Tangent looks very similar to x cubed, except that it's periodic. That has symmetry with respect to the origin, so that is odd. Cotangent is displaced from tangent and goes the opposite way. It has symmetry still with respect to the origin. If you look at reflecting this upside down, if you draw it on a piece of paper and turn the paper upside down, it still looks like cotangent, so that is also odd. Even though it doesn't go through the origin, it doesn't have to go through the origin, it just means you can rotate it around the origin. Secant will have the same symmetry as cosine. So secant reflects over the y-axis, is even. And then cosecant has all of the properties of sine. Cosecant has asymptotes at x equals n pi or pi k. Same thing. Zeros, none. Symmetry, odd. Okay, so those are our 6 basic trig functions. And then I told you last class that we would take a look at inverse trig functions and put an exploration tool on the topics page so that you can explore it. You can kind of play with turning the graphs on and off. So we start with, in this one, the blue graph is sine of theta. So the blue graph is sine of theta. And then what I've done is the red graph is sine of theta reflected over y equals x. So that yellow line is y equals x. Now remember, that makes an inverse graph. However, we want our inverse to be a function, so it must pass the vertical line test. Now that red graph does not pass the vertical line test. So what we do is we take part of it that would pass the vertical line test. Now, if I'm looking at this graph and I want to take part of this to pass the vertical line test, our temptation is to take the part closest to the x-axis, but notice that still fails the vertical line test. So we shift up a little bit and we take the part above the x-axis. So this part in black here is the graph of the inverse of sine. This is sine inverse of theta or x. Okay, now if we're looking at that in terms of the unit circle, that falls between, it would go right here, quadrants 1 and 2. So whenever you take sine inverse of something, it's only going to give you a quadrant 1 or a quadrant 2 answer. Same thing happens for cosine. Our second graph here, the blue is cosine of theta. The red is reflected. over the line y equals x, which is in yellow. And again, we have that red graph would not be a function. We want it to be a function. So what we do is we choose, say, the largest part that is a function. And so that happens to be this part right here, right around the origin, which is ideal. And that is quadrants 1 and 4. Quadrant 4 and quadrant 1. And our last one, arctangent. To find arctangent, we would take our graph of tangent, which is in blue, reflect it over the line y equals x, and we get all of those red ones. Well, that's not a function, but at least for tangent, there's a very clear way to select the part that will be a function. And that is to take just one iteration of that shape, one period of the function. And that is how we get tangent inverse of theta. And that is also quadrants 4 and 1. Okay, so sine, we couldn't take the same quadrants. We couldn't use quadrants 1 and 4 for all three of our trig functions because for sine, quadrants 1 and 4 don't make a function. The inverse of quadrants 1 and 4 are both positive. Okay, so we had to use quadrants 1 and 2 for that. This is very similar. It should kind of make you think back to when we talk about the definition of the square root function. If I take the graph of x squared and I reflect it over the line y equals x, what we get is this shape, which is not a function. So then we choose to look at the square root function as only the positive ones. And then we said, if there's a negative root, we'll just put a negative in front of the calculation. So very, very similar. Finding the inverse trig functions is just like this when we discovered the square root function and defined it. Okay, now we don't have like secant inverse because what we would do for that is we would first convert it to cosine and then use cosine inverse. So you're not going to need secant inverse. You would just take secant, convert it to cosine, and use cosine inverse. Now, again, sorry, I've realized I keep saying again. So for the purposes of these calculations, we're going to have plenty of time to practice actually calculating with them when we come back from break in second semester. But the purpose of this was just to define them. You may not have seen these inverse trig functions, so I'm showing them to you so that when we come back from break, when we see it again, your brain will have had some time to kind of digest it and think about it a little bit. And then when we come back from break, we'll do more practice and a more formal kind of definition and using all of these functions.